Hello, good morning. This is my new project. It's an Arduino powered data logger. Now what I'm going to be using this for, or what I intend to use it for, is to put on the solar panel to monitor current and voltage of the panel throughout the day. Log it to a memory card, and then we can do graphs and stuff and say over an entire year what the performance of the panel is doing. So on here, on the display, you can see I've got volts and amps, although the amps look about right, 0.4 amps, but the voltage doesn't look right, 984 volts, 7 volts, sorry. I'll go over quickly how the code works and I'll adjust that voltage. Oh, there you go, you just saw. What this does is every 60 seconds it saves a file to the SD card and it comes up with that message on display you just saw. But every second the display is refreshed to give you a live update. So you've got time, current, voltage, and the date. And then on the board here you've got an Arduino Nano, which is the brains of the operation. Got a real-time clock, which is giving us the clock, date, time information, so we don't need to row in code about time, we just get the time off that. This is an SD card module. And then over here is a current sensor. So this is what the current is measuring. And this is just an analog value, so it goes into an A to D. The voltage at the moment, I've just got a LDR just to experiment with, but that's also in an A to D input. The real-time clock is I2C, the memory card is SPI, and the display is just all on digital pins with its own library. So the code isn't too bad, it's just using a load of libraries to control every single bit, and then you're talking to them individually. But what I'll do is I'll show you how I'm going to be intending to use this, and how I'm going to adjust that value to give it a more sensible reading. So I have here a DC-DC converter module with voltage going into it. I think I've got 10 volts going into it at the moment, and on the output, which I'm holding here, I've set it to 5 volts. So that is going to be the DC-DC converter that I'm going to use to power the circuit. Let go of this, let's shorten it out. On here, I've got on the output, that's going to go straight to the data logger, and the input here, I've got a tap coming off the input, going through a 100k resistor, then going through an 18k resistor. So in here, this is going to be our differential point. So this is going to be a potted down version of our input voltage. So we're measuring. I'm going to use the data logger to measure its own supply voltage from the panel. So this is being supplied from the solar panel. So if I block the camera quickly and put some meters in, so I'm now measuring the potted down voltage. You see, it's 1.5. Well, it was 1.55 volts. Now we turn the input voltage supply up. Right, so I've just turned the input supply up to 20 volts, and on the output now, or the potted down resistor, we've got 3.16 volts. So that is a safe value to plug into our Arduino ADC, because of course you want to keep it under 5 volts because it's a 5 volt supply. So we pot down the input voltage because I've got 20 volts coming in, so that we can measure it, and then we will scale it to give us a display of the input voltage. So what I need to do is take some readings of the input supply, the potted down voltage, and the value that I'll get on the display. So now I've added some more wires, and it looks even more of a mess. What I've got here, I've got the input voltage being measured by this meter. Then on display, you can see the hex value. Sort of, come on, focus. So on display there, you can see the hex value. So this is just a raw hex, no maths being applied to this value being shown, and that corresponds to the supply voltage. So down here, we had 258 and the supply voltage of 8 volts. So if I turn the supply voltage up to say 20 volts, you see the hex value is rising, and that'll do. And you can see our supply is around about 20ish volts. So now all I've got to do is just do a top value and a bottom value of what the supply voltage is and what the hex value is, and use the map command to map them figures together and produce a linear response for the voltage. roughly 10 volts, we have a value of 308, 311, yeah, call it 310. I'll change that to 310. So that is 310. No, that's not very good. I know what I mean. And 20-ish volts, we have a value of 627. Let's go with 627. So, oh my word, 627. So these values I'm going to use in my code, which I'll show you now. My code, and as you can see, I'm using a lot of libraries. So I've got Crystal, Wire, which is I2C, the DS1307 RTC real-time clock, the time library, SPI, and SD card. So lots of libraries, but they do make the code a lot easier. Obviously, that's what libraries are designed for. A couple of variables there. This will define the LCD, so you've got to define what pins you're using for the LCD. So in the begin, so simple, just start up your I2C, start with your SD card. Now there is where I'm using the analog. This is where I'm getting the values. So here, this is actually the read value is what I'm using for my voltage. So it's just quite simply an analog read. That's why at the moment the display is very simple. And then this is what I've done for the current at the moment, is I've got a raw value where I'm mapping the analog input, and then these are the maps one. So the analog input is from 510 to 603, and it gives a range of 0 to 4.6 amps. So it's 4.6 amps. Then we divide that down, because it's 460, by 100 to give us our 4.6 amps. And that's the range. I'll do something very similar to the value, which is the voltage, and similar along this sort of lines, and then you see what the result that gives us. So now I've changed the code, so we are mapping the values. So we map the analog input 0, which is where we're taking our reading, and we've got 10 volts and 20 volts, and then we've got the two hex values that we receive. So the first hex value is hex value for 10 volts, the second hex value is the value we got for the 20 volts, and then we then take that value and we divide it by 100, and we use that as the value we want for the volts. And that's the same as what we've done with the current as well. Although with the current we've had to offset it slightly. Well, not really, it's exactly the same, yeah. So it's exactly the same method for the amps as we have for the voltage. And yeah, then we get our two, hopefully, accurate readings for voltage and amps. And we'll put it back on. So what it's doing at the moment is we've got a fairly sensible reading, with it floating away. You touch it, it goes up. So it looks like that's working. We shall put it back on the jig and we shall see if it actually performs. Clearly made an error here because we got 10 volts as our input. We are reading 0.96 volts. And if we turn it up again to 20 volts, you can see we're reading 1.99 there. So there's a bit of discrepancy. I think what we need to do is divide it by 10, not by 100. But you learn from your mistakes, and this is one that I've made. So we'll change this value of 100 to 10, and we'll see what that does. Upload. Value changed. We've got 10 volts on the display, 10 volts on the meter. I mean, there's a bit of difference. We can play the values to tweak it a bit better, but that's the basic idea. So we put the voltage back up. I know. 16.1, 15.4. Again, it's a bit out. I mean, like I say, we can go over and change them hex values to get a more accurate reading. But that's the idea. So 20.6, 21.3. You sort of see where I'm going with this. But yeah, I mean, this design can be changed, and this idea can be converted to anything. So this design doesn't have to measure a solar panel; it can measure anything you want. So it's very adaptable. Just change the code to suit. And like I say, all this is being logged every minute to the SD card, so we can build up a graph and everything, and it saves it in a normal Excel spreadsheet. Alright, thank you.